Okay, so yeah, welcome to the second lecture of deep learning and neural network. One minor comment from last time. It seems we had a small error in the derivation of the sigmoid function. I tried to correct everything in the slides. I hope it's already uploaded. But yeah, I mean, everything there was in that way explained correctly. It's just like we took as given the one derivation, and that wasn't the correct one. So if you read it again or listen to it, don't surprised if there's two things now different. For today, we'll do a bit of an excursion as a preparation to dive deeper into the neural networks. And we'll look a bit into what hardware we are currently using to do to train deep neural networks, what software we are using in order to a bit understand that. Because when we are then in the next week explaining the different network architecture, we'll see that there is a strong connection between them, and therefore it might be good to understand some basics about what type of models we are using. So this shouldn't give you a deep overlook on like what is graphical computation and so on. There is a lot better lectures on that at KIT, but I try to give you a very small glimpse into it with what I assume is important in order to like make you better understand how current state-of-the-art neural networks look like, why some decisions are taking, and so on. One important thing is that, I mean, the big advantage of neural network and machine learning is that we can very easily get better. You can normally just get better by having more data and having larger models. And especially making this larger neural network is really not difficult. So we have seen that the last time. You don't have to invent a great new thing, how to make things larger. You just copy your model, you add another layer, and that makes your model often a bit better. But of course, this is also, of course, only possible if you have a good infrastructure. So if you can run these large models. Therefore, it's important to think about making them efficient and running them. And also what we'll see later for the other part of the infrastructure, the software. We talked last time about how backpropagation works, and it's important to understand them. But hopefully today you will also see that luckily you not always have to think about all these things, like how to you really calculate the backward path and so on. So you have to do that a bit in the practical part. It's there to get you a bit of understanding. However, when you're really using the techniques, often you don't have to do that. And we'll see there is ways of automatically doing that, which of course gives you then also a lot faster type of building the models. You don't have to think about it. You can maybe think of more complex ones. And that is therefore also important to keep in mind. Furthermore, this type of infrastructure is also like has a bidirectional influence. On the one hand, the better infrastructure you have, you can just build larger models, your models get better, and you can have really large improvements. So definitely one reason why nowadays we have so good working neural networks, and maybe it wasn't that well in like 40 years ago, is because we have more data and we have more processing units. It's one factor which you cannot really underestimate. And that, of course, makes it also possible to have new ideas. I mean, there is this idea that, yeah, if you have some idea, you implement it, you test it, we always have to test it. And yeah, there is like maybe you wait one day for your results, maybe 1 week. But if it's taking longer, you can't really do progress. So you only will invent stuff which can be somehow tested in a week or something like that. But also there's another way also, like with the knowledge of what can be currently done with architecture, it's also that we will develop models which just fit very well to the architecture. So, I mean, I guess you all have already heard a bit about these transformer models, which are used everywhere, which we'll cover. But one big advantage of them is that they can be calculated very, very fast on GPUs. It's like, I mean, they are really good and they're a great idea, but they might not be super much better than some other architecture. However, if this architecture is just easier to calculate, it's better adapted to the hardware, then you can calculate more, you can train on more data, and your thing will work better. Therefore, it's good about to know a bit about how neural networks are processed on a computer that you can develop later. Maybe if you have the idea and you want to develop some new layer or something like that, you should be aware of that. And in order to efficiently really use them, it has to fit to your hardware. And yeah, therefore, we'll today cover mainly two areas. We'll look into GPUs, and it's really, really like very basic, but it's a bit like what we are doing. We already started to introduce that last week. So we started, or like the typical thing, what you're seeing of neural networks are always these nice graphs which are connected. But when you then look into program code, you might be surprised. What you mainly see is matrix multiplication. And last time we already a bit like showed you the connection, and we'll do that more today, because that is really essential. Because you can, in addition, like to show things as these graphs, you typically can show them as matrix multiplications, and this can be done very efficient on GPU, and that's why you can calculate them very fast. And for example, that might be also like why we are currently very good in working with dense representations, so with networks where there's weights to each of them, while there is a lot of work on like sparse neural networks where most of your values will be zero. But if you hopefully later, when you have thought about how things are done on GPU, you'll see if you have a lot of zeros, you still have to calculate them all. And that's why it might be not super efficient doing that. The other part we want to look at, the second part of the lecture, is on automatic differentiation. So at least get an idea of like how we can automatically do the backpropagation, so that you typically nowadays in frameworks we look at like TensorFlow, or like we mainly do PyTorch, you don't have to think about the backward path. So what you define is your model architecture. So your model, how the model is calculated. And then on the backward path, this is all done automatically. You don't have to yourself do that. Of course, again, it's important to know the basics. I hope I have again motivated that already. Last week, we saw about that, for example, for the activation function, you have to think about that it's like a meaningful derivation, because otherwise there is no good learning. So it's good to understand the basics, but luckily you don't always have to do everything in detail. So what are we talking about here? This is what we had last week, and this is like how a very basic neural network, everything we have done until now, is looking like, and we'll look into this today in more detail and see how we can calculate all these things. Just as a remember, so what we have is we have an input with a fixed size dimension, an n-dimensional vector. Then we have our weights, which connects all our inputs to all our outputs, and this is fully connected. And that's, again, something, for example, which we'll see is just working very well in GPUs, because there we anyway have to calculate all of them. And so it somehow makes sense to have all of them and not have like sparse connections or something. Then you have your hidden layer here, which is the weighted sum of your input. We do an activation function, and then maybe more layers. And then at the end, we have our output layer there at the end. And that is, yeah, how a network does. I could imagine if you're now if your task is to implement that, you're not thinking about hardware or anything, you're just using your programming skills, you might do some calculation like this. So you're going all your ranges n and m, you're summing up always your hidden state as the weight times the input, and then you're applying your sigmoid function on top of that. So you have two interleaved loops here, which go over all possible weights. You sum up the weights times the inputs, and that. I hope most of you would have done something like that, or any. Okay, that sounds good. So you have all your things there. So what is to think about here? So what we have to do is we have to do several jumps. So you have always a loop run, and if you know how a loop is, it always has to check and either go further in the loop or jump somewhere else. And if you think about CPUs and they do try to pre-calculate things, so it might be that in the end this is not super fast, because if you go like there one by one through it, if you're out of one loop, it does a misprediction. It's not doing again inside the loop, but goes outside and so on. So it might not be like the best and most efficient way to do the calculation. Because there's one thing, while there is several jumps in there, if we really would do that as a matrix, everything is deterministic, so clear what to do. So you're doing mainly the same operation a lot of times. So the calculation you do for each entry in your of the output of the is exactly the same. It's like the matrix multiplication, which is a row times a column, and this is all the time the same. The only difference is that you have different indices to do that, but the calculation for all your outputs is the same. This is now for one. Here we're talking about one single matrix, but you have to assume a large neural network. You're doing that over and over again. And so it might be that we could do things more efficient. And we already talked about that this can be shown differently. So you can also view this as a matrix multiplication. So for one specific K, for one specific hidden unit, it's a vector multiplication. And if you then want to do all of them in parallel, it's mainly that you have the weight matrix times your input vector, and that is your hidden representation. And if you think like that, then there is not really a loop anymore. It's like one way of calculating things. And it's mainly this type of matrix multiplication. And maybe it's already indicating you that there's other types of hardware which are significantly better in doing that, and that are GPUs. So let's briefly go into that. So when we're thinking about CPUs, again, a very, very high level, they have several of your calculation units, the LUs, and they have quite a complex control logic, and they are optimal for a lot of optimized for a lot of operations like if and for and so on, which you use in normal programming. And of course, we are getting increasingly more cores like that, but still that is somehow limited. And each core can do a lot more than just pure calculation. While what we saw here in our calculation, when we do a matrix multiplication, we don't need that very complex control structure. It's not a complex control structure. It's mainly you really have to do just a lot of multiplications and additions and so on. So when you think about that, so we have a fixed serial sequence of computation. For when you do the matrix multiplication, it's fixed beforehand what you have to do. For every output entry, it's like the row times the column, and that will be the entry. There is no branching, so it does not depend on which values are in there. The calculation is always the same. Doesn't depend on whether here's a 0 or a 0.1 or something like that. It's all the same type of calculation, which of course is, again, remember that when you design new layers or so, of course, what we're talking about, which makes things good, is that exactly we have these type of condition, that there is no condition on how to process. The calculation is the same for all type of inputs and all types of weights. It doesn't depend on that. So there's also no branching. And another important thing, you can do there are a lot of things in parallel. So each of your values for one layer can be done in parallel, and they don't depend on each other. If you think about that back on the graph, it very nicely shows you which are the conditions, and you see that the blue ones only are conditioned on the previous ones. They're not independent of each other, so you can calculate all of them in parallel. And then the red purple ones at the end, they depend only on the previous ones. They also not depend on each other. So if you go, yes, you have to go from left to right here. You cannot do that in parallel, but the calculation in one column here can all be done in parallel and is independent of each other. So yeah, where can this be done, or where is this also happening? And there's a very, very different, complete other area where something similar is also needed. And that's maybe a bit surprising, but if you think about a graphical rendering, something very similar is happening. So the task is, you have as input somehow the description of a scene, like the surface is three-dimensional, and you have which materials in there, what is the light condition, and then you want to have an image of the scene. And there the algorithms are somehow similar. You like have to calculate what is the color of each of the pixels, and the calculation of each of these pixels are also independent of each other, can be done in parallel. And this war is, of course, very important for if you think about computer games and so on, where that is done, and dedicated hardware was developed for that. So if you have played with some computer games, you know there is the GPUs, which are important to get a fast and good user experience, and they have to do very similar computation. And that is one big step for current deep learning models, that we can use these GPUs to do the calculation. And since you're seeing the big progress in deep learning, since there were the first attempts to put neural networks and calculate them on GPUs. Why is that happening? The architecture of GPUs is quite a bit different. So you see there's just a lot more cores in there which can do the calculation. And so you can do a lot of like parallel computation in there. It's dedicated design to do all these. However, because you cannot get that for free. I mean, if you just could build more and more and more cores, I mean, you would do that in a CPU also. The difference is that each of them has a lot less capability, has fewer capabilities, and therefore they all typically have to do the same thing. So they are especially efficient if you can do these types of calculations, where you do the same calculations for a lot of data points. So it's called, I mean, if you're having some hardware thing, it's like the single instruction multiple data paradigm. So you have a single instruction and you want to apply it on a lot of different data points. That is exactly what we have to do in neural networks. We have one instruction, which to, for example, do a matrix multiplication, then we have to do it for all our elements in the thing. So this is like, originally they were, of course, even more extreme. Nowadays, the GPUs get also more complex, but still is a little bit, it is different. There's also like merging things, like when you think about like the Apple thing, but still keep in mind that this is something we want to design. So if you're developing your neural network architecture, the idea is that you have one operation which you can apply a lot of times, and it's the same for everything you're doing. Yeah, what is the difference? It's here a bit shown by some numbers. They might be a bit older, but you see the big difference. So while the CPU has like 10 cores, here you have 10,000 cores which can work in parallel, and that makes it possible for the right application that you have a significantly higher possibility to do the computation. And we'll see later some more slides on, like, if you look how expensive it is to do calculations, that this got cheaper over time, and you could just therefore build a lot more models, because if you can just do this more of computation, it's working a lot better. Another, like, then you of course can extend that. There's one thing which is mainly used by Google, which is even more efficient. You don't know exactly how it works, but there's TPU. I guess you've heard of them, which are specifically designed for doing the inference of the models, and they are even more efficient. So how does it come, and what do I have to do to run code on your GPU? Let's do there a bit of rollback, how it originally was happening, and then we want to look at one quite simple single example where we do just the addition of two matrices and how that can be done on a GPU. So originally there was this graphics shading language, which allowed you to extend your applications to like implement how specific materials should look like. And so you could invent your own materials and that they would look differently. And how that works is that in the rendering of your thing, in between, at some points, you could add your own code, which would then apply it to all pixels of that. So you could map into the general structure of how to render pixels, and you could add some code that you could implement new ways of how things should be developed. And that would be implemented, like run then on all pixels. And the first way was that you really were like somehow hacking this type of software. And so the first application of a GPU was that, okay, now we're just creating an image, which is, for example, 500 times 500, which is our output. And then the code we are doing is that we are running our code for each pixel. So you're looking at your input like as the input to the GPU, and the output matrix, the output weights will be output code, and you're like in this shader programs, you're running your code, and that will be executed 500 times 500 times. So you can do this calculation very fast. This was at the beginning, of course, more of an hack, but since around 2002, there's the extensions to GPUs, to general purpose GPUs, where you can now write specific code and where you can explicitly use GPUs to do these types of calculation. So we don't have to do the whole hack with a pipeline here for graphics, but you can directly use it for doing machine learning models. How that works, first on a high level, so there is dedicated code for non-graphical applications, and to be honest, I guess most of graphic cards by now are no longer used for doing graphical applications, but they're used for other things. Of course, they're also used for Bitcoin mining and things like that, but machine learning is an essential part of that. And the idea is you have on the one end the host code, which is the code which is running mainly on the CPU, and then you have specific code which is run on the GPU. How it then works is you allocate some memory in the GPU memory, you copy your data there, and then the application is run on the device. That is the kernel method, and that is like how one element has to be calculated. So you're not describing the whole matrix multiplication or matrix addition in the device code, but it mainly says like for one matrix element, how should you do the calculation? That is your device code. What you can then do is you provide this device code, and then you tell the application, the GPU, to run this code n times for how many times you need it, and that can then schedule that and run that all in parallel. Of that, of course, is like a very high level, a lot of simplification in there, but this is more to what is somehow important for at least a basic understanding. There's a lot more like how to efficiently share the memory on the GPU, how to efficiently transfer data, especially when you think about matrix multiplication, you have to look at one row and one column. That's getting important with some, like how you store the data, whether it's row-wise or whether it's column-wise. because then you can more efficiently load the data. You don't have to wait that long. We'll not look at these details, but it's more on the high level idea is that you're not like writing for loops how to go through that, but the main idea is, can you somehow write a code which is then executed for all of your individual things to run or to efficiently do the calculation, because this can be all done in parallel. So it's at least not as important then anymore whether your matrix has 1,000 or 5,000 entries. Of course, there are limitations. Not everything is optimal parallelized, but the difference at least is no longer as big. Before we are looking now into the example, are there any more questions about the general idea? Good. Then, yeah, still do the example, and maybe things getting clearer or less clearer, then let's see. And so we'll do a very simple example. It's like you do a matrix addition. So you do matrix A in blue plus matrix B in purple is should be matrix C in green. And we want to calculate matrix C. For example, we have here small sizes like 12 and 6, but you'll see how that is doing. So how can we do that? First, the math is quite easy. This is super simple. What we have to do is our result is just the element in your one matrix plus your element in the other matrix. So it's one simple addition, and you have to do that, but for all elements. So it's really like everything can be done here super in parallel. You can do that independent of all your other entries. You don't have to care about that. And we can like do all these calculations in parallel. So again, it's something which is perfectly fitting to this type of GPU calculation. And therefore, the first thing we want to look at is like now the node code. So the code that is run several times. So what is the kernel, the real code that is run on the GPU to do exactly this type of calculation? It's not difficult math, so it's quite easy. We somehow need to know which are, like, if I'm a thread, I need to know for which entry in the matrix I'm responsible, and then I can do the calculation. So if there is a thread ID, for example, so each time I run the calculation, I know for which one it is, then I can divide it by the size, and also like to get the row and to get the column, I do the modular operation. So I have then A, I, and J out of that, and then I can easily do the calculation. That's all I have to do. And this is then all the things, each of the things. So this has to be then called, of course, 12 times 6 times, and you always just do exactly the same calculation. In real GPUs, it's done, or not. I mean, there are several things, but one thing is you often have tensors in this calculation, so 2-dimensional or more. So what we typically do is our index is also 2-dimensional, then things get even easier. So you're just getting an X index and a Y index, or maybe more, even a Z index, so 3-dimensional, and then you're doing the calculation. It's only you don't have to fiddle around with your index. Then there is one more thing. It's not that all threads are somehow the same. There is some hierarchy in that typically. So you have your threads, let this be threads, but they are grouped into some blocks again. So here you see you have 12 threads in this example, for example. These 12 threads are blocked in groups. So in total, you need 6 blocks of each one, 12 things. There's a lot of things to consider with this about like how they are parallelized. What about data loading? So you can optimize there a bit or a lot. Again, for our explanation, it's just this exists. The basic and most important idea first is that we have all these 72 parallel threads running there, and each of them is doing one element of your matrix. Given that, then of course you have to consider that, so you don't get typically a thread ID, but you get a thread ID, which is only within your block, and you get a block ID. But again, based on that, both of them, you can easily calculate the index you're working on, and then you can do your calculation. So this is all the code that you have to do for doing a node. If you really want to see the code, this is an example of that. So what we're seeing here is then exactly the code. So this is like CUDA code. So you're defining your kernel, which is a matrix addition. What it gets as input is these three arrays where your input is and where the output would be. Then you have to calculate on which element you want to use. So which element you want to add in this thread based on your block index and your thread index. And then you're just doing the addition, and that's it. So 3 calculations here, and that can be done then for all your elements in the matrix in parallel. So that is what people call these types of kernels, which are then run on the GPU, and where you have a lot of them all performing things in parallel. The next question is then how to run the host code. That's then even more like easy. So you say how many threads you want to have. Again, we're doing that in 2 dimensions. So if we have our matrix, which is 12 times 6. So in our case, we have 12 threads times 6 threads. And then we are saying, do this matrix addition of A, B, C, and with 12 and 6 as the X and Y index, so 72 in total. And then we send this to the GPU, and we're waiting to finish this calculation. And then hopefully you have the full calculation. That's the other part of your code. How that looks like is again here. So you say how big your matrix is. You say how many threads you want to have. So how many threads per blocks. And then based on that, if you say you want to have 4 and 3, so 12 threads in one block. And given all your entries you want to have, it's clear how many blocks you want to have. And then you'll trigger this execution here with the matrix add, and that is all your code. So when designing this code, of course, you have to think a bit different. So especially when you started doing things with if and so on, it might be counterintuitive first, because you might otherwise here also sometimes do extra calculations. So typically what you have to do here, you have to do that for everything. But things are a lot faster because this can be done mainly parallel, at least independent of each other. Of course, you have a limited number of threads on your GPU. So if you have more threads started here than you run them on the GPU, it takes waiting. You need to copy data and so on. But things are a lot faster, and you can do this calculation significantly faster. Yes? This is these types where you block your threads into like a hierarchy. So you have a block of threads, and then in totally all your threads are the sum of all your blocks. There's on most GPUs, there's some type of hierarchy. It's also for them to schedule them. We don't have to go into the details in this, but it's more that there is a hierarchy of how you index your threads. So the total number of threads is the number of threads you have in one block times the blocks you have in there. No, I mean, each thread might not be even running really in parallel. I mean, you can define here more threads than there are cores on that. But I think there is some correlation to the physics. And if you want to optimize things, you have to think about the physics of the GPU. But again, this is for a deeper good. Any more questions to this? So, I mean, just, always keep that in mind that you try to make things in parallel. That, of course, here it's super easy with a simple matrix multiplication. But if you now think about it, you have the output, then you want to get the most probable index. So you want to take some of the max index and so on. So things get a bit different than just looping over it with a for loop and finding the maximum. There are often ways of doing that. You just should always keep in mind when you implement stuff that it's a lot better to not like loop through your matrix, the results, or to your input, but trying to do it in a matrix multiplication or tensor way, because these things can, because of that reason, be done a lot more efficient than that. There is like one example we now wanted to look, or we'll look onto, which somehow directly connects to that. And that is like where you really don't typically do the looping, but you try to do things in parallel. So what you hopefully have now learned is we have this single instruction multiple data approach. So we try to do the same operations as often as possible, because that is just more efficient. And one important thing you now learned is that you can do this, that you're doing this matrix times vector operation to get your hidden state. So if you now look at that, the question is, can we do things can we even increase the number of same operations that we can do? And so does anybody already have an idea how you could even make things more parallel than this? So you take one input, you multiply it with your weight matrix, and that's your output. Maybe especially if you think about your training process, where what we saw is we are taking one example, we are calculating the backpropagation, and we are looking at the next example, again doing backpropagation and so on. Yes? Yes, that is exactly the idea. So if you remember the training, you put in one example, you run it through, you calculate your error, you backpropagate, then you have your gradients. But normally you're not directly updating your gradients, but you're doing that for several examples. You're always accumulating your gradient, and then you're doing the update of the weights. Because if you look at one example and say, oh, I should go then in this direction, it might be quite noisy. Like for each example, it will show you in some other direction. So normally it's good to do some type of averaging. You could do the really extreme by going over all the training data, calculating the average, and then doing the update. But of course, that's very, very slow because there's huge data. So normally you do some trade-off that you're looking at 100 to 1,000 examples or something like that. Then you're averaging your gradient, and then you're doing the update. And then we are seeing that we can do maybe this one even more efficient. And that's because of GPU, and that's what we're doing. So we can change this into a matrix multiplication. So from a vector matrix multiplication to a matrix multiplication. And then we can even do more things in parallel. So instead of looking one example at a time, so always putting in one example, calculating the output, we can just look at several examples in parallel. And if you do this matrix multiplication, the result will be the same as if you do like 5 of the upper one matrix vector multiplication. So that is what people refer to also as batching. With batch, it's a bit difficult. There's two different meanings. Sometimes people call a batch like how long it takes until you do an update. So how long you accumulate your gradients. And sometimes it's like the batch size of the GPU, like how many things you do in parallel. They are connected, but it's important to keep in mind they are different. But however, hopefully you see here directly how the use of the heartbeat detector also like influences how you implement. So if you would do like a normal, like non-parallel thing, it wouldn't make sense to like process all in parallel, but it would be like as fast to just do one after the other. But with this parallel processing, it now makes sense to instead like look at all the examples in parallel and run them all in parallel, or at least some of them in parallel. Of course, I mean, now the question is, why don't we do like all our training data together? However, there is, of course, some limitation. Somebody has an idea why it's not the best to just put all your training data in there and run it all together? Yes, exactly. So there is a limitation of the larger the batch size is, of course, the faster your calculation is, but the more memory is also needed. You have to store all your input and you have to store all your output. And with very, very, very large data, of course, that's no longer possible. So you have to, there you have some computation limitations in the batching that it somehow you should not have too large batch sizes, because then they don't fit anymore in your memory. So that is the one type of limitation. But there's even more types of limitations. The other thing is logical. So on the one hand, it's training. So of course, during a batch, you cannot update your weights. I mean, you do the same operation on all your training examples. So you cannot update your weights in between because you're doing it at the same time. That means the batch size has to be smaller than how often you update your weights. And that, of course, depends on your model. What is a good one? How fast you want to converge? How complex your model is? But you have to keep that in mind, that when you're training, of course, you can only update after a batch. You can do it after each batch. You can also, maybe it's better for stable reasons not to do it after each time, but after only X times of that. But it has to be like one multiplication of that. This is, of course, not only helping in training. It's also an important idea to do the same thing during inference. So also when you inference, of course, it might be nice that you're not running only one example through it, but you're running 5 examples and doing the prediction. I mean, also at least some, like the time might be less, but especially if you think about companies, they're once training a model and then they're applying it hopefully for millions of applications. And then you need a lot more computations by inference than you need by training. And then it's, of course, also nice if you can save computation time and do the inference in parallel. But here, the question is, are all your inputs available at once, or do you have to wait for them? So if you think that it might be that, yeah, you process a full batch together, then you can do that. But if the things come in one by one, then of course you can't do that, and you have to do normal processing. There is a third one, a model limitation, which might be not important at the moment, but you should keep that in mind. Currently, I mean, if you do that, all models, all examples need to have exactly the same form. So we have to have the same dimensional vector here. It cannot be that one input example has a different size than the other. Now you might be wondering, we said that this is one important condition for networks, that you have as input the x1 to xn, and it's always the same. That is true. So this limitation for normal feed-forward networks, this is not a problem. But I just want to hint that already know, because if you think about other architectures we'll cover, this will come up. So if you think about a recurrent neural network, which processes a sequence, you'll have sequences of different lengths, and then it might no longer be that easy to do this batch process. I mean, people will still try to do it, and there's ways, but you have to think about it. And again, like that means what type of algorithm you use is also partly driven by the implementation. So this only works to like process several things in parallel if all your input examples have exactly the same form, so you can do exactly the same calculation for all of them. Okay, so what does it mean to have some numbers here? So these are like graphic models, VGG or ResNet, and you see the difference between like running it on a CPU or running it on different like GPUs. You see that it's just like these networks are really like 60 to 70 times faster if you run it. And that's why currently like most large scale neural networks will be trained on some of these GPU hardware, and they can be only done efficiently in this way. So it's really like important to not only view the networks in the graphical structure, but also think of them in the metrics writing, because that is how they're implemented at the moment, and how we can like fast and good calculate. That this is important, maybe also a bit shown here. So this is on different architectures, how expensive it is to calculate some amount, so gigaflops per dollar. And you see that with GPUs, we are getting more efficient, and we see a clear rise that we can very efficiently calculate large models, while the rise in CPU is less, and only because that it's possible to train the larger and larger models in there. Like Tensor TPUs are even more efficient, but here you see very nicely that it goes up, and only because you can do this very, very large type of calculation, you can build large models which show then the power of these type of neural networks. Good. Before we are going a bit to the next part, any more questions? Yeah. Well, yeah, like how many floating point operations that you can do. So how many operations? Good. So there is still one limitation which we want to talk at the end now a bit about, and that is like you sometimes even have to think about more, because models get more and more and more and more big, and there is one limitation which we haven't talked about at the moment, is that your model should fit into the memory of your GPU. Because in order to do these calculations, of course, the model has to be in your GPU to do fast calculation. And this is no longer possible with large current state-of-the-art models. And that's why then people looked into, okay, how can we use multiple GPUs to even train them? I mean, maybe they don't fit in, or it's too slow. So also GPUs are fast. You have large amounts of training data. So there's two problems. Could be your model is too big, it doesn't fit on the GPU, or it just takes too long to like iterate each of your examples, and you want to use several GPUs to do that. And we'll introduce a bit of like different techniques, how you can split your data, or you can split your model in order to facilitate then several GPUs to do that. Any basic idea how you would do that if you have another task? You're happy, you're having 5 GPUs. How can you make your model bigger or your algorithm more efficient to use all of these? Do you have already an idea? Any idea? It's quite, you have large amounts of data. You have a large model, or like I have a small model maybe at the beginning. Now you have many GPUs. What would you do that you're not doing everything on one GPU? Yes? That's one very good idea which you can do first. So instead of running all the data on one GPU, you split your data, then you put your data to different GPUs, or like part of the data. You run your forward-backward path, so you calculate the gradient. Now the extra work starts, because of course nothing is for free. There's no free lunch. So you want to keep all your models synced. So of course it shouldn't be, if you can now update each of the models, then your models will get more and more different. But that is not really helpful, because then you just have in the end 3 models which are trained on 1/3 of your data. So what you have to do is then aggregate your gradients to calculate then the update, and then you have to distribute them again so that they all keep in sync. But what you can then easily do now is that you can calculate everything in parallel, and so you can do, efficiently, hopefully use multiple GPUs and speed up your process significantly by doing that. What about the update size and batch size in this case? Any restrictions, others than before? Yeah. Yes, that's definitely maybe a good idea, because then they are somehow in parallel, as the one batch is a lot larger. then the others have to wait for the update. There's another thing about, if you think about the update size, how often can you update your weights? What is the minimal update size? Yeah. Yeah, exactly. After aggregation. So now it's not, before it was that we can update after each batch. So if you process 10 examples at the same time, you can update after 10 times. This times you do 10 in GPU 1, 10 in GPU 2, and 10 in GPU 3. So it's 3 times your batch size, and afterward, then you can update. Normally, that is not a restriction, not super important how often you do that, but you should keep that in mind, that of course you can only update here when you distribute your weights. So you can only update if you have seen, like, if everybody has calculated all of them. So the advantage is the idea is very easy. You just copy your model to each of the GPUs and then process always one part of the data there. The advantage is we can do parallel computation, which means we are getting faster. Of course, it has also some disadvantages. On the one hand, we have the communication overhead. So you'll not be n times faster because each GPU has to wait for the others, which hopefully is not long because they do exactly the same thing. But you also have to send then all your updates to one general GPU, calculate the update, and distribute it back. So there is some calculation by that. Furthermore, it only works if your GPU really fits on one GPU. If your if your model fits on one GPU. So you cannot use that if you have a very large model which doesn't fit on the one single GPU. But I mean, most of the case it might be fits, or you have to buy a bigger GPU to do that. But at least it's one way. You can easily extend that. So this was assuming that typically you have all the GPUs in a single node, so in one PC. Of course, you can easily extend that to having not the GPUs in a single node, but you have a network with a lot of servers, and each of the servers has several GPUs, and they all work together. The main idea is exactly the same. The advantage is we have more GPUs. The disadvantage is typically communication is slower between different nodes than between different GPUs of the same PC. So this overhead gets even more, and you have to wait even longer to do that. But in principle, it's mainly the same idea. There's nothing, clearly different between them. So what can we do if the model doesn't fit really on one thing? And there is this idea of zero-power data parallelism, where the idea is we have even more overhead of communication, but it's done efficient. And then we are not storing the model on all GPUs, but mainly each GPU is storing part of the model. And then every time it needs to calculate, it gets the parameters that it needs from all the other GPUs. So they distribute them, and then it calculates, and then it can delete the parameters again. And then, I mean, you have to think about this is typically not for small models. Like, I mean, if you have one layer, that doesn't really make sense because you still have to store all the layers. But if you have now hundreds or more layers, like you always have to, you're only like using 1% of all your parameters at one time step. So you're getting this 1% during the calculation, and then you can delete it again. And so you're not needing all your parameters everywhere, but you need only to store one ends of your parameters, hopefully in the end, to do that. It's called zero-powered data parallelisms. And it's, again, the idea that, you're storing only what you currently need, and all the other things is stored on the other GPUs. There's a bit of different versions of that. We can have a bit of a look at that. So you have here n GPUs, and in the baseline, what do you need to store? So the main things you have to store is your parameters. You also have to store your gradients, of course. I mean, you do the gradient calculation, so you have to store them. And we'll come later to that. When we do the optimization, it's often a bit more complicated than the simple formula we had, where we just do like some hyperparameter times the gradient. So you have to also store some states of your optimizer depending on that. As shown in the baseline, you're storing that on each of the GPUs. So the number of parameters you have is you have to store plus like once for the parameters, once for the gradients, and then once from the optimizer state. When you're now doing this type of sharing, the first thing is that the optimizer state, which needs most of the GPU, most of the calculation for large one, you're storing them only like at one GPU. So you're not storing it everywhere, but one part at GPU, the first part at GPU 0 and so on, and you see the last part on the GPU. So that's the green part. So now you have a lot less memory. So you see before the model was like 120 gigabytes on each GPU, and now it's only like 31 gigabytes on each GPU. And now you can, of course, extend that. You can also store the gradients only partly, and you can also store the parameters only partly. And in the end, you have that there's only like 1% of the data is used, and the rest is distributed. So it's significantly more optimized than it was before. So that is the main idea of these zero-powered data parallelisms, that you're not storing everything on the GPU, but you're like on demand loading the parameters that you need, and the other ones are not needed and can be distributed. Any questions to that? Then there is another, again, more simple thing. First, if your model is too big and it can't fit on it, the first idea is maybe you can split your model up, and that is called model parallelism. So the idea is, just imagine, for simplicity, you have your 2-layer neural network with 2 layers. They don't fit on your GPU. So more realistic, this will be 100 layers, and 50 layers fit on the one GPU. So what you can do is split the model in 2 parts, the first 50 layers and the last 50 layers. And then you give your data on GPU 0 to the neural network, calculate all your hidden states until you're at level 50. And then you're transferring the data once from one GPU to the other GPU, and then you're doing the rest of the calculation. So now GPU 0 has to store half the model, and GPU 1 has to store half the model, and that's all you have to do. So that seems to be, quite straightforward in some way to do that. Do you see any problems with this? Why it's this easy might not be the best way of doing it? Yeah? Oh, sorry. Yes, and even more extreme. Then GPU 0 has to wait till GPU 1 has to finish, and so on. So, and this is only for 2. So if you think about, if you have 4 GPUs, the first GPU 0 is calculating, then GPU 1, then GPU 2, then GPU 3, and then all the way you do the backward pass, which has to go in the other direction. And then you can do the updates. So this is nice. Here things are done in parallel. But if you look at all the other time, it's like as efficient as having just one GPU. So it's all the time only one single GPU is running, which of course is not what we want to have. I mean, we're using all the memory efficient, but the calculation on, we pay a lot for 4 GPUs, and we're not really faster than one single GPU. So that's not super exciting. Maybe from other more hardware-oriented lectures, you have an idea what you could do now? That's exactly perfectly the solution. So it's pipeline parallel. So you split your data into smaller parts, and then you're processing that. You still have some, of course, non-working thing because you have to wait, but exactly you have to do a lot less. So you're splitting in 4 parts maybe. Then while the GPU 0 is calculating the second part, GPU 1 can already calculate the first part. Then in the third step, GPU 0 is calculating the third, GPU 2 the second, and GPU 3 is doing the first one. And this way, you're seeing very nicely, hopefully in the image now, GPUs are a lot more busy, and you still only need part of the resources, so that is good. But this is just then a lot more efficient in this way. Yes, there is one thing where you can even try to do things parallel on a single matrix. It's called tensor parallel. So if you have very large matrices, it's sometimes even good to split them up individually. So what we are normally doing, X is our input, then we have our weight matrix A, and we are getting our matrix Y out of that. And what you can, of course, also do is you can split your weight matrix in 3 parts here, have them on 3 different GPUs. You do the multiplication, then you have on the 3 GPUs each of the values, and then you might have to join them again. It's called tensor parallel, and for very large parts, that is partly also done. You can also see that then on larger networks, so the full neural network. So instead of doing if you want to do here a normal MLP, which is some activation function, and then the input times our weight matrix, we split our weight matrix into 2 parts, A1 and A2, and then we do the calculation A1 on GPU 1, A2 on GPU 2, and then you get the 2 results, Y1 and Y2. You can even have some more layer if you have afterwards a dropout exactly the same. You can do that further, and then you do that at the end, which does the calculation. So with this, you can do some of the calculation also more efficient or like distributed. Yeah, there is some general hints how to do things. Just so there's of course a lot of different situations. So if you have a single GPU and the model fits on the GPU, it's a nice, easy solution. Just do the normal use. So the model doesn't fit on the GPU. What you can do is you can do things like the 0 one, but now you don't have multiple GPUs, so you cannot offload to another GPU part of it. But what you can do is like put part of your parameters always on the CPU and always only load the parts which you need. If you have a single node and multiple GPU, if the model fits on a single GPU, you can do distributed DP, for example. If it doesn't fit, you can do 0, for example, or tensor parallel. Then there's also multi-node, multi-GPU. It seems that often 0 is working quite well. You can also do something pipeline and tensor parallel, and they're all that together. But one issue with tensor parallel is that you have to like implement things very different. You cannot just do it the same way as you have done it before. So it has to be, your code has to be modified to work that well. Good. Any more questions to the hardware? So this was a bit, yeah, an outlook at on what we are running the GPU. And I hope you already got an idea why we talked about that, because like things like batching and so on, they're influenced by how we are running everything on the GPU. And from the time-wise thing, you hopefully also have seen that it's really essential to run things on this fast hardware, because then we can just build a lot larger models and doing things more efficient. And for deep learning, that is really essential, because the easiest thing to improve your performance is to have more data or have larger models, and that you can, the best way do it on very fast hardware. Yes? This is like the one PC where all the GPUs are, or if you have several PCs where there's like a lot of GPUs. So normally you have some limitation. At least at the university, we have a maximum, I think, of 8 GPUs per node. And if you want to use more, then it's, yeah. Good. So then after hardware, we'll also look a bit into software. So when we look at that, one thing you always have to do if you implement neural network from scratch, you implement on the one hand your forward pass, which is like somehow defining how your architecture is, because that is exactly how you do the calculation. But then you also have to implement how you do the backward pass, so how you do the derivation. However, these are quite fixed rules. So if you know the forward pass, it's clear what the derivation is, and you don't really have to implement it again and again. And you saw this nice modularity. So how you calculate the derivation in the first layer is the same as you did in the third and the fourth and the fifth layer, because your gradients are just flowing back. Therefore, the question is, do we really have to implement that all the time over and over again? And the good news is, with current software architectures, you don't have to do it. So this is normally done automatically. And what we want to look is how this is done and why. How it is done is with what people refer to as a reverse mode. So you define your model as a computation graph, where each computation is very simple operations like adding and multiplication and so on. And for each of these type of elements in the graph, you have a rule how to build the derivation. I mean, if you add two elements, it's clear how you define the derivation. If you have a multiplication, it's also clear. Even if you have some specific activation function, it's also clear how the derivation can be calculated. And then the nice thing is we have the chain rule. If we are like in the graph, do all the operations one after the other, then we can do the chain rule, and the derivation is just a multiplication of the different things. So what we can do is we can do the forward pass. We have to store our internal results, because often the value is important to calculate the derivation. And then we can calculate the backward pass and collect the derivation and calculate all the derivation one by one on the way back. And yeah, this just is therefore a lot simpler, because we don't have to care about how exactly to calculate the derivation, done automatically. Of course, we have to keep in mind it needs to be calculated. So we only can take operations where this thing is well defined. So yeah, have a very small look on how that looks. So we could have in one layer neural network, we would have this type of computation graph. We have as input our x, our input, and our weights. What we are then doing is the product of both of them. Then we have an activation function, and that is the result of that. So this is a very easy, straightforward computation graph of that. Then you can now look, how does that look in code? So the forward pass is quite easy. You have maybe the value here in between. We call it k. So k is x times w. And then the second calculation you do in the second node is your output is sigmoid from k, which is 1 divided by 1 plus e to the power of k. And that is everything. So how do we do the backward pass? And then we're going backward, and we have to always apply our rule. And the chain rule was that the derivation is the local derivation times the derivation that we get from the backpropagation. So the gradient at the output is 1, the gradient at k is, and the gradient at the output times, and now the gradient of sigma we had it was sigma k times 1 minus sigma k. There you see now, here you put in what you stored. So you have stored sigma k out as your when on your forward pass, so you know the value, and then on the backward pass you can just reuse it. So you have to store this values that you can then on the backward pass use them to calculate the gradient. Then the gradient w, so you have to take k. If you calculate the gradient to w, it's x, so it's the gradient from k times x, and the gradient x is the gradient from k times w. And that is how you calculate that. See, I mean, for this simple example, it's not super complicated, but we already see, yeah, we have to do quite a lot of calculation then. The forward pass is normally easier, and you need less thinking than you have at your backward pass where you have to do the calculation. The nice thing is now with automatic differentiation. These are all rules. I mean, we define them so that we don't have to do. And so in things like PyTorch, this is all you have to do. You say O dot backward, and then everything is calculated backward, and this is done automatically. How that works, I think, is hopefully is clear. I mean, we have the fixed rules for all the nodes, and you apply them, and you don't have to implement that themselves. That can be done automatically. So this, of course, makes then training these models a lot easier because that works just this easy. The only question which is then still open, normally you're not programming this graph. Normally you have your code, and somehow we need to generate this type of graph out of the code. And that is like the graph creation. And there is two main ways of doing that. The one way, which we'll first look, is what people refer as a dynamic graph. So that means that this computation graph is calculated at runtime. So it's not that once you create the graph and then it's done, but during runtime, you will create the graph and then do the forward and the backward pass in that. That is in that way nice that you directly execute the graph, and it's for debugging reasons, it's often a lot easier to do that. That was at some point one very nice feature of, for example, PyTorch, where you can do that, where you use dynamic graphs. Is also, we'll see that later. Now we are saying the network structure is always the same. In reality, it's not always the same. Then it's also easier that you can build different types of graphs, and you're just more flexible. Afterwards, we will see that there is also the possibility to have static graphs, which you once build and then use for all the time, which has the advantages of it might be more efficient, but of course less flexible. Not very recently, but somewhat recently now you can even do both in PyTorch, so you can compile once your code. But for debugging, I can just say that often this type of graph is a lot easier. So how does it work? So we have here a very simple type of neural network. So we are iterating over a lot of examples. Then we're doing our prediction, which is we take X, we do a matrix multiplication with W, then we are like squashing it somehow. We do a second matrix multiplication, and then we are calculating here the loss as the difference between the prediction and the weight. So this is a bit like the clamp. It's like for 0, it's 0, and for the other one, it's linear. So the clamp is a ReLU unit that we had there. So this is your code. So you have an input, you have an output, you have two metrics, and you have the activation function in the middle. So you have a two-layer neural network where you do that, and in the end you do your prediction, and you have here the loss backwards. So you don't have to care about how to calculate the backward pass. That is done automatically. So how does in this example the dynamic graph work? So first we are creating our objects. So we have the input, we have the output, and we have the two weights here that are our variables. And then this is somehow defining the command how we define the graph. So what are we doing here? We're taking X and multiplying it with W. So you have in the graph X and W1, and you do the matrix multiplication. Based on then you do the activation function, which is your clamp, which you have in there. Then you do another matrix multiplication with W2. So you take W2 and the output and put it here. And this is then your resulting variable, our predicted output. So this is the first part of your graph. And then you're of course not only doing you're building the graph, and in parallel you're also doing the forward pass. So you're not only saying this is how it's calculated, but here you really have the value in there. You're doing your prediction already here, and in the end here you have the value of your predicted value. Then you're doing the second time, which is calculating the loss. So you do minus of these two, so the prediction and the y. You do power of 2, you do the sum, and this is then your loss that you're getting. So this is your final loss. So this is, again, you're building your graph, you're extending your graph dynamically, and you're doing your forward pass to do then the full calculation. And then somehow the magic happens, the backward pass. So then you have this graph and you can do the backward calculation all the way, that's loss backward, and you can calculate your loss and store, if you do loss backward, what you normally do in your weights, which you have marked. Here you see nicely require grad. So it's marked that for these objects, you should store the gradients that you then do the backward calculation and store all your gradients in there. And then why is it dynamic? Now the one is deleted, and the next time you go over your next example, you have to recreate your graph. So afterwards, the graph gets deleted, and you can create another or the same graph and so on. But so it's not that the whole graph is there all the time. Any idea why this could, for example, also be of advantage? I mean, somehow it first seems a bit unnecessary, yeah? We can use conditions. Yes, that is very, very important. The other thing is, of course, we might have not to store the full graph all the time. So we don't have to store everything on the GPU all the time, but we could store something outside and we can be more efficient. And of course, as I say, it might be that the graph is not always 100% looking the same. The other idea is to build a static graph. And there the advantage is that typically you can do things faster. And there are two reasons for that. The one reason is that you don't have to rebuild the graph all the time. Of course, yeah, creating the graph also needs a bit of time, so that you have to do all the time here over and over again, while in the one you once create a graph and that's done. But there's another reason. Once you have created the graph, there's also then algorithms to maybe optimize the graph. So you can then optimize your graph, and then the forward passes maybe even faster, because there might be rules of things, how you can do things in parallel or different. If you once have a static thing, you can do general optimization algorithms to make these things fast. But it also comes, as always, as a cost. The one thing, typically, this type of debugging gets a lot more complicated because, then just everything is run through it and it's no longer clear where exactly the error happens. And if you have dynamic data structures, things aren't that easy. It's possible, but not that easy. If you think about if your input is no longer a fixed sequence, but for example, if you're working with text and you have different lengths text, then this might be complicated and not that straightforward. Good. Any more questions to that? Good. Then we're today a bit faster. Let me just briefly repeat what you should keep from today. So as I said, this was a bit of an excursion, but hopefully I could motivate you why it's important to have a basic understanding on which one we are using the GPUs, and that you should also keep in mind how neural networks are implemented on GPUs, why we're doing it, and why it should be faster. That sometimes we will have models that are so big that they can't fit on a single GPU. So we also have to think that when building our models, how can we make them efficiently to maybe distribute over different GPUs and so on. And the other thing is the implementation wise, that it's important to understand the thing of derivation and how we backpropagate the gradients. However, the nice thing is we don't have to always do it. But if you build a real GPU and use the right software, this can be done somehow automatically. If there's no more question, then thanks a lot for coming and see you again on Tuesday.